Okay, so let me let's recall the change of variable formula before the proof, as I told you last time, involves some work. It's not immediate like in the one variable case. So, but here's the statement. Notice an interesting thing here. In this formulation, we first talk about the change of variable function rather than the function being integrated. So here it is. So T from E to Rn C1, and here is the assumption which is really not needed. T prime x is invertible for all x in E. As we'll shortly see, this is the same thing as saying determinant of T prime x is not equal to 0 for all x in E. Then now we come to the function which is being integrated. F from Rn to R continuous with compact support. Support of F is contained in image of T. Which is open, by the way, since I've assumed that by the inverse function theorem, this is T of E is actually an open set. Then here's the actual formula. So then integral of f of y dy on Rn is equal to integral of f of t of x again on Rn multiplied by determinant of t prime x absolute value and then dx. So this red thing is not going at all. Okay. So that's what we are aiming for. So this thing. Now the strategy of proof will be the following. Basically, this function f is not so, I mean, it's just a continuous function. The key thing here is this t. There are some strong assumptions on t, namely that t is actually, the t prime x is invertible for all x. This is a very strong assumption. Now, well, strong assumption in some sense, not in a different sense, it's not so strong. But the point is, the proof proceeds like this. You prove this formula, whatever we have here, if t is of a certain kind, if t is kind of rather simple function, depends on what you mean by simple, but you'll soon see what exactly we mean by that. Then this formula is valid. Then you try to prove it for every t which has this property, t prime x is. Oh, I forgot one crucial hypothesis. This is the strong assumption, not t prime x is invertible. T is 1 to 1. This is the key assumption. So 1 to 1 invertible, and then you have this. So you prove it for certain classes of functions t which satisfy 1 to 1 and invertible, t prime x invertible. Then you try to prove it for everything. We have already seen one way of one instance where we did something similar. Remember when we showed that in the definition of the integral, the order of integration does not change. We proved it first for functions of a special kind, then we proved it for all functions. We use the for that we use the Stone-Weierstrass theorem. So here it's not quite the Stone-Weierstrass theorem which we'll use, but something else. We'll see. But as I said, first of all, for this we need to talk about determinants, because it makes a crucial appearance here. See here, the determinant appears. One value of the determinant, a very important thing about the determinant is that it will help you detect when a matrix is invertible. You just have to calculate a single number, the determinant, and then you immediately know whether the matrix is invertible or not. That's quite a remarkable thing, but that's a sort of qualitative thing. Here, it's not just that. We actually need the value of the determinant in the integral. So we have to look at it in some detail. So let us see. So last time I started this, and let's proceed where I had stopped off. So remember that yeah. So what did we have? We have J1, J2, Jn is an ordered n tuple of integers, and we had talked about this as J1, J2, Jn. It's just the sign of the permutation determined by these integers. If we assume that all these Ji's are between 1 and n. Right now we are not assuming that, so we really can't talk about permutations. This is more general. So this was product of Jn sign of Jn minus 1, sign of Jn minus J1, and so on. Actually, I could have just put the sign on the overall thing, J2 minus J1. And then, so then we define if you start with a matrix Aij, determinant of A was defined to be summation J is J1, Jn. Here, each Ji lies between 1 and n, and the index I also varies between 1 and n. And then A1, J1, An, Jn. And we have proved these properties that determinant of the identity matrix is 1. Then determinant is n, what is called n multilinear. Oh, actually, I don't think I had proved it. I just stated it. I'll prove it now. The n multilinear determinant of x1, xn. So here xi is something, xj is something. Remember, we had introduced this notation, the determinant of x1, xn, where x1, x2, xn are column vectors, is by definition the determinant of the matrix A, where A is x1, x2, xn. x1 is x11, xn1, etc. So this says that if I interchange any two columns, keeping the others as they are, so this is actually, Rudin doesn't mention this, but this is called skew symmetry. So this property is called skew symmetry or alternating. So these 2 and 3 together say that the determinant is an alternating n multilinear form. This is the technical term which we don't need, but if you study this kind of thing, there's a whole theory of bilinear forms and multilinear forms. This fits in that context. At any rate, these are not just some random sort of ad hoc properties. These are very natural properties. Now let's see why this is true. I won't do it in detail. I mean, it's just so the first one is A equals identity. Then we have AII equal to 1, AIJ equal to 0, if I not equal to J. Well, so if you in the expansion of the determinant, there's only one term which will survive. Namely, see, every term looks like S, what was it? J1, Jn, A1, J1, An, Jn. So, excuse me for a second. Yeah, sorry. So let's this thing. So, well, every term is of this form. So the only way a term can survive is J1 equal to 1 and Jn equal to n. So you'll get S of 1 n A11 ANN. Now this thing, by definition, S of 1 up to n, where was this? This will be just 1. I'll put n minus 1, etc. All terms are plus ones. So I'll get 1. So not much more to be said about that. Then multilinearity. So what does multilinearity mean? So what it means is just that as a function, we so this is the way we think about it, determinant of this. So this multilinearity property just means that if I fix n-1 variables, any n-1 of these xi's, then it's a linear thing with respect to the one which is not fixed. So for every I, so for example, the first one would be determinant of alpha v plus beta w x2 xn is alpha det. Oops. Actually, the square bracket, okay, fine, doesn't matter. So x2 xn plus beta so this is what it means for all alpha beta in R, VW in Rn. So this is what we want. So let's prove this. Well, first of all, linearity involves two things. One is that scalar multiplication can be brought out. The other one is vector addition. So the scalar multiplication part is clear. So clear that determinant of alpha A by the way, I'm just focusing on the first slot. I mean, just to keep notation simple. Obviously, the same thing, whatever I'm saying, will work for any xi, not just x1. Clear that this part is holds just by definition, simply because every term will be of this form. Now, every term is of this form, and well, the point is that the only way this will survive, yeah, actually, this is one observation which has to be made right here. This is constantly going to be used. If and only if no two of the, this we already observed, no two of the j's are equal, i.e. if j1, j2, jn is a permutation of 1 to n. So this is always has to be kept in mind. So all these J1, J2, Jn, they're just permutations of 1 to n. So there's no repetition whatsoever. So that means that every term in the formula for the determinant in the sum will have exactly one of these A terms will be only one of these terms, one and only one will be from a given column. Of course, the same consideration holds for rows as well. Rows, it's even more clear because it's the row index is anyway prescribed to be 1 to n. So exactly one, you pick out any term in the sum, look at the product of the AIs, AIJs. Only one of these n terms will be from a given row or a given column. So that immediately makes this part clear. So if I put an alpha in one of these columns, that alpha will come here for that particular element from that column. The others will remain as they are. So there won't be any higher powers of alpha. Right. So we just have to focus on in a formula forget the scalar. That part is clear. By the way, I'm being a bit sloppy about square brackets and round brackets. So normally when here round brackets would be preferable because if I want to think of that as a function from Rn cross Rn to R. So in that case, this round bracket makes more sense. It's an n-tuple Cartesian product and it's an n-tuple. Each entry is an element of Rn. So I want to look at this. Now again, the same consideration will hold. Whatever we just discussed. If you go back to this thing here. For instance, here I've taken the first column. So now I'll be every term in the determinant is J1, Jn, A1, J1, An, Jn. So pick out any term. Look at the part which is coming from the first column. It might be something here. So let's say AK, JK. JK would be is equal to 1. You look at that column. But AK, then AK1 would be just V. So V would be V1, Vn, Ws, W1, Wn. So AK1 would be Vk plus Wk. And all the others would be the same. All the other columns, all the other AI, A1, J1, etc. correspond to these other things, other columns. They have been left as they are. Only here we have added two things. So I'll get this. And here there's a sum. So this each term will split as a sum. So this will become this J1, Jn, A1, J1, and then Vk Actually, it's kind of messy to write down all these things. And a similar thing, S J1, Jn, A1, J1, WK, and this. Well, right. So this, but if you notice, this thing here is the same as the corresponding whatever term you would get in determinant of V x2 xn. The expansion of this will contain precisely this term in that place. And similarly, this term would arise from W xn. So a term by term analysis meaning just looking at it, actually, you don't have to do anything. You just look at each term in the determinant and you will see that this whatever we want holds. So that proves the multilinearity part. And what about the alternating property? Well, so here what one would like is right. So determinant of x1, xi, xj, xn would be minus determinant of x1, xj, xi, xn. Now, what you do is you just work backwards. You start with this right-hand side. So let's introduce new vectors, y1 equal to x1, etc. yi equal to xj, the others are the same. Yj equal to xi, yn equals xn. So what we are looking at, somewhere along the line, I replace this capital D by small d. So this is my convention. People use both notations. So let's don't get confused about that. Det equal to det. One with a capital D, one with a small d. Right. So I have this, and where was I? Yeah, okay. So I'm looking at y. Well, so you have this J1, Jn, Y1, J1, Yn, Jn. So x1. Now you have to watch out for. So yeah. So I can't quite. So let me just say it in words. Here in this y1, j1, etc. Obviously, all the way the y's were defined, the vectors y were defined, they're all the same as the x's, but except two of them have been interchanged. Likewise, here in the sum, all these except two of these numbers, all the others will be the same as the corresponding terms in the if you start with the x vectors. Now, two of them will be different. The only thing you have to remember is this thing here, the index. Because how this keeps S, the S factor just depends on the index, not the actual value of the y's. So what I mean to say is, for every term here, I can set up a correspondence with, let me use K1, Kn. Yn, Kn. So this is determinant of x1, x2, xn would be like this. And what I want to say is, every term here, there are n factorial terms, remember, in this sum. Every one of these n factorial terms corresponds to one term in, exactly one term in this upper sum. And how do they correspond? It's just that it is the same, except that the sign is changed. So how do you see that the sign has changed? It's just that, well, yeah, and what is the correspondence actually? So here, obviously, if I look at the term corresponding to Sj1, now instead of Ji, oh man, I made a mistake. This J has already been used for this index. Now here I can't use J. So let me use, say, P. P. Right. Then now it's okay. P1. Pj, Pi, Pn. If I look at the permutation which is like this, then I'll get all the corresponding x's will be the same. So, oh, this was supposed to be actually, here it was x. Rather, let me look at here. Here, if I look at S K1, Kj, Ki rather than Ki, Kj, then I'll get this part will be the same as this part. They're literally the equal. If I consider this S1, X1, K1, and then Xn, Kn. Okay, simply because of this flipping around business. So if these indices are interchanged here, this term will be the same as this. So, but, and all these terms do occur in amongst the n factorial expansion. But this thing here, so now all you have to notice is Sk1, this you have to check actually, it's a combinatorics thing. This part I won't do. So you have to check that this is the same as minus S K1, Ki, Kj, Kn. Again, if you use the permutation interpretation, this is very obvious. All you are doing is you are taking a permutation, multiplying by a transposition. After multiplying by transposition, obviously the sign of the permutation will get reversed. That's precisely what we are saying here. But rather than using that interpretation, I want you to check this directly using the definition of S that I have given. So check this. So at the end of the day, it just boils down to a property of the S function that we define. I spelt it out in great detail, but still it might not be clear. I can't help you there. You just have to go through that. This is one of those things where you just have to look at it in detail. As I told you, it's combinatorics. The theoretical part is very minimal. You just have to see what's going on and you will get it. So that proves that. So as a the corollary is that if I if I take det of x1 xi plus xk summation cj xj j not equal to I and then xn. This is the same as determinant of x1 xi xn. So what I'm saying is that if you add a certain linear combination of other columns to a given column, take the determinant, you'll just get the determinant of the original matrix. That's all. And the proof is, first note that det of x1 x2 xn equal to 0 if xi equal to xj for some j, for some I not equal to j. This is an immediate property. In fact, this is equivalent to the alternating property. This is an immediate corollary of this. If xi equal to xj, then the right hand side, even without the minus sign, will be equal to the left hand side. But there's a minus sign. Therefore, both sides have to be equal 0. So that's immediate. Because of this property and the additive property, the multilinearity property, what one gets is, so determinant of x1 xi plus summation cj xj j not equal to I. The multilinearity property will tell you that this is the same as x1 xi xn plus summation j not equal to I, determinant of cj, I can again bring out x1 xj xn. Okay. So I've taken the sum over all these. There's one plus here and there's a whole bunch of pluses inside the sigma sign. So I just split it up. Well, right now each of these terms is 0 because there's an xj here, but the j is not I. So this xj will, this is the ith slot. So the place where xj is occurring is the ith slot. But we have an xj instead of xi. So that same xj will be occurring elsewhere. And because of 1, each of these is 0. So we have this useful thing which we are all familiar with. See, I'm just going over stuff which I expect all of you know already. But we don't want to assume anything. So let's, other than basic stuff about real analysis. So I proved this. Now we come to a theorem, which is determinant of BA is determinant of B times determinant of A. Again, this is one of those things which appear just by virtue of familiarity. It seems like there's not much to prove, but if you actually try to think about it, It's not obvious at all why this is true. After all, the formula for the matrix product is kind of complicated. On top of which there's this complicated definition of determinant. If you naively start to write down things just going by definitions, you'll get nowhere. It becomes a horrible mess. So you have to think of some indirect way of proving this. And here's one way of doing it. So what we do is, let's define, oops, took the wrong pen. Fix B, let's define a map delta B from Rn, just like the determinant, with a twist. This is going to be, it'll act on n tuple of vectors I define to be determinant of BA, where as usual A is this matrix made up of column vectors x1, x2, xn. As I said, it is just the usual determinant function with a twist. The twist is that instead of just taking det A, I take det of BA. So for each B, I get this function. Now, the columns of BA are Bx1, Bxn, right? I mean, after all, how do we figure out the column vectors of a matrix? Well, you just think of the matrix as a linear transformation, act the matrix on the standard basis, see what you get. So to figure out the columns of BA, you would be calculating things like this: BA E1, BA En. These are the column vectors. But this is the same thing as B of AE1 is x1, AEN is x1. So that's how you get this. So we can relate, we can write. So therefore, this new function delta B, which we define to be det of BA, is the same thing as determinant of Bx1, Bxn. I mean, we haven't done anything here. We've just written it in a slightly different form. That's all. But this way of writing things makes one thing clear there, which implies that this function delta B has properties. See, we proved 3 properties about the determinant as a function of n vectors. First one was determinant of identity A is 1. Second one was multilinearity. Third one, oh, where did the third one go? Oh, it was already here, I think. No. Third one is here, the alternating property. So now for this new function, I leave it to you to check. This way of writing things as det Bx1, etc. immediately makes it clear that This new function has properties 2 and 3. Multilinearity and alternating property. If you interchange any two, if I interchange xi and xj, I'll get a minus sign, etc. Obviously, the first property will not hold. If I take identity, then I won't get 1. I'll end up getting det b. So I have these two properties, and so let's write it out. So delta b A is delta b right. We start expanding this. By the way, I'm sort of switching back and forth between the A. So when I think of A, it's the matrix Aij, but in column vectors, it's x1, x2, xn. So this x1 would be A11, AN1, etc. So the point is that, yeah, this x1, for instance, would be A11 in terms of vector notation. This would be AN1, En. So here we'll write it like this. AI1, E1. So this is the same thing as summation. Because of the multilinearity property, I can write it like this. A I1 delta B EI x2 xn. And then you can keep repeating this. So repeating meaning what? Instead of x2, you would write it in terms of the basis vectors and the coefficient, some AIs. Again, use multilinearity. Expand. So you do it for all x2 all the way up to xn. So repeat for x2 xn. So you, after n steps, you will end up getting a. But then the notation you'll have to change a bit. See, as long as you're expanding only the first one, the index I was okay. But now for each of these xi's, you will have to have an index. So let's, I itself will put something, I1, 1, IN, N, and then delta B, EI1, EIN. Okay, so now the alternating property which we have not used so far will imply that, let's look at all these terms, delta B, EI1, EIN. EI1, EIN. We already said that delta B is an alternating form or function. So that means if two of these are equal, it will be, rather, if I flip any two of these, I'll get acquire a minus sign. So what I can do is, and that will force if two of them are equal, actually, if the same index. So for instance, if EI1, or rather if I get something like this, E1, E1, etc., it will be 0. So we just have to, yeah. So what we do is, basically we write it as, we can assume that all of them are distinct, otherwise it will be 0. So, but if they're all distinct, again, like so if I1, the only way it will survive is if this thing, this is a permutation of 1 to n as before, then it will be, only then will it be non-zero. But if it's a permutation, what I can do is, I can just keep switching them around a pair at a time, so that I get E1, E2, En. But I'll acquire a sign here, which I don't care what it is, I'll just call it Ti1 up to In. So in fact, I do this where Ti1 up to In is 1, -1, 1 or -1 or 0. So I don't even have to remark that these are all distinct. If they are not distinct, I'll just put this t function to be 0 if any two of them are equal. Even then this equation will be true, because right hand side is 0, left hand side is 0. If they're all distinct, then I can't arbitrarily put a value for t. I'll just have to see how many times I have to flip. Then it will just become the sign of the permutation, actually, so that I end up with 1 to n, which is the identity permutation. So essentially this t is the sign of the permutation, if it is a permutation. If it's not a permutation, if the indices are not a permutation, so if there's repetition, then I just put t equals 0. With this, then what happened? Let's go back here and see where we were. This, I had ended up with this expression here, and I was just trying to simplify this term. So delta B x1 up to xn, now I'll write as what was, oh, of course, this AIs were there. So I'll put the T as well. T I1 IN delta B E1 En, and then this usual A, where was this? A I11 I11 A I10 N. Actually, I'll put this, let me just write it in a slightly, I'll put this one first, and the A I11 A IN N delta B E1 En. So this is delta B E1 En, anyway, is just a fixed term, times this T I1 IN A I1 A IN N. Preetham, you want to say something? Are you, somebody is, yeah, I think it's Preetham who's typing something.
Okay, sorry.
Okay, fine. No, I was worried that some of the video feed might not be, might have stopped or something. Now we are almost done. So basically, yeah, by the way, what is from the way we have defined things, this delta B E1, En, what is this? Anyone?
Determinant of B.
Determinant of B. Because remember, this was just determined by definition. This is determinant of B times identity, which is determinant of B. Oops, why did I go there? So this part is just determinant of B. Now, what about this stuff here? We don't know what this is. No, I mean, actually we know, but only thing is, see, this almost looks like the determinant of A. The only thing is when the determinant of, for that, you'll have to see that this T function is the same as the S function. You'll have to prove that. And moreover, there's a slight problem here. When we define the determinant of A, the sum was over columns, not rows. Here, notice that the index is occurring in the row. I1, I2 are in the rows, not in the column slot. So there is that issue. So one can resolve it that way also. I mean, it's not difficult to directly prove that this is the determinant, but there's a clever way of avoiding even that calculation. Namely, what you notice is that this thing here, whatever you have here, is actually, it doesn't depend on B. This T calculation, for instance, this T function, of course, doesn't depend on B at all. It is just a matter of this I1, I2, In, what kind of permutation it is. And of course, this A's have nothing to do with B. So this is something which is independent of B. So even if I call this a constant of A, let's call it some phi of A, something involving A. Then what I have is N is determinant of B times phi of A. Oh, actually, hold on. Oh, sorry, not even, yeah, sorry, not, this is not x1, xn is phi of A. We had fixed B in the beginning, but this holds for any B, for all B and A. For that, to say it holds for all B, it's important to make this observation that this whatever stuff you got here actually doesn't depend on B at all. So I can use the same function phi like this. So this is true for all B. So now you take B equals I. Then what you get is delta I x1, x2, xn, which by definition is the same thing as determinant of IA equal to determinant of A. And on the right side, I'll get determinant of I times phi of A determinant of I is 1. So phi of A is det A. So through this clever observation that I can change B, I straight away get phi of A equal to det A. I don't have to, like I said, one can also directly prove that phi of A is det A just by looking at this formula closely. and then proving that determinant of A is same as determinant of A transpose, etc. But the cleverer way is like this. You just make this observation that this equation holds for all B and A. And then you're done. Okay, so we'll stop here.